And yes, I am live. And today I am late for this YouTube live chatting app making building stream. So let's just begin. And today I wanted to check out all the things that there are in the all the configurations that I can do in my router. So let's see what are the things that I can change in my router. I don't know if I should be making this public or what, but it doesn't matter. So this is the dashboard, CPU utilization and memory utilization, which makes me think that a router is just a computer that is specialized in doing specific things, which is well, which is expected, but it is still amazes me that it is just like a simple computer. Let me just ask ChatGPT and talk to it about it. And yes, so in this section, this area shows me that user 3%, CPU utilization, that the kernel is taking up 9% of CPU, 89% is idle input output, that is, I guess, Ethernet or um, landline. They are not connected, so internet input output is taking 0%, and the users who are connected are taking 3%, and memory 47% is occupied, and the rest is free. Okay, so this is just a computer who is doing specific things just like a normal computer with some CPU and memory, which is very specialized in a very specific thing. Application, accounting, TR. Okay, is this are these the applications that are running? Okay, and some more things. Device status, version. This is the version of the hardware physical device. Okay, this is series, model number, and wireless. The things that it supports wireless. Okay, SSID and SSID 5G. Uh-huh. Wireless clients. I clicked there, and that says these are the wireless clients who are currently connected, and these are their MAC addresses. This is, I guess, the MAC address for my device, uh, 55, 75, and 76. MAC address in WAN, that is okay. But before that, yes, the router in my house is just a normal computer with a processor and memory, and is continuously running some programs uh, which have been very fine tuned to perform a small number of tasks, uh, which include routing, switching, DHCP, handling, etc. How about that? Let's see. Yes, that is exactly right. Your router is essentially a specialized computer designed to handle networking tasks efficiently. It has a processor, CPU, typically a ARM or MIPS based chip optimized for low power consumption and fast packet processing, memory, RAM, or flash storage. RAM for temporary data or yep, routing tables, and for temporary data, and flash storing firmware, the router's operating system, and flash for storing firmware. The routers operate, yeah, it must also have a operating system and kernel and stuff. A firmware, okay, firmware OS, a highly optimized OS like OpenWRT router OS or vendor-specific firmware that runs programs for routing. NAT is Network Address Translation, DHCP, Dynamic Host Configuration Protocol. Firewall, well, firewall which stops some requests, which acts as a reverse proxy and blocks some requests which you want to block. Interfaces, WLAN and LAN ports, Wi-Fi, radio. Hardware components that handle network traffic between devices and the internet. Interfaces. Interfaces, does this mean interface for the device from the device's perspective, or like interface which the router has to communicate with the devices connected to itself and the internet, or the interface which it provides to the devices which are connected to it? I guess this is the interface which it provides, which the router provides to the devices which want to connect to it. WAN, LAN ports, local area network, ports, wireless area network. I don't even know fucking full form of WAN. Hardware components that handle network traffic between devices and the internet. Because routers have a very focused job moving packets efficiently, their software is minimalistic and fine-tuned for performance and security, but at core, they are just compact, dedicated computers running network software. Some high-end routers even let you install custom firmware, turning them into fully programmable networking devices. Right. Okay. WAN and LAN. Okay. WAN, full form. Wide area network. Wide area network is the simplest form. A wide area network, WAN, is a collection of local area networks. A collection of local area networks or other networks that communicate with each other. That is what Cisco says. Okay, a collection of subnets. Uh-huh. Uh, LAN refers to a subnet network connected through a switch, and WAN refers to a collection of subnets which are connected through a router. Is that correct? Question mark. Yes, that is a good way to think about it. Well, isn't that the way to think about it? Local area network. LAN is a network within a limited area. Example: home, office, or campus. Devices in LAN communicate directly, often through a switch which forwards packet based on MAC addresses. Based on MAC addresses. Okay, MAC addresses belong to the device. A subnet is typically used within a LAN. Uh, a subnet is typically used within a LAN. Okay, meaning all devices in that subnet share a common IP address. Okay, the fact that devices share a common IP address is called subnet, but LAN does not always has to be implemented through a subnet. Okay, wide area network. WAN is a larger network that connects multiple subnets LANs over a wide geographic area. The router connects different LANs and forwards packets between them based on IP addresses. Yep, here we use IP addresses and we use a router. The internet is the largest WAN made up of many interconnected networks. Okay, internet is the largest WAN. Internet is a WAN. Okay, so in your house, your LAN consists of devices connected to your router via Wi-Fi or Ethernet, and your WAN connection is how your router talks to the wider internet, typically through your ISP. Another way, typically through your ISP, which means that my router forwards the request to the ISP, which to the local ISP, which sends, if necessary, sends the request to national level ISP, which can send it to a global level ISP. And there are a few global level ISPs, and one global level ISP sends that request to another global level ISP, and that communication between two ISPs which are not in the same group is handled by Border Service Protocol, BSP, right? BSP, uh, Border Gateway Protocol, Border Gateway Protocol, Border Gateway, because it is a gateway through a border, and of course, it is a protocol. So in your house, your LAN consists of devices connected to your Wi-Fi and through your ISP. Another way to summarize, switches keep traffic within LAN. Okay, what is MAC address? What is MAC address? A MAC address, media access control address, is a unique identifier assigned to a network interface card. Network interface card of a device. Wait a minute. I have something. Shit. Yep. Oh fuck. Uh-huh. Did I lose it? Nope, I cannot. I cannot be that stupid. Share. Um. Uh-huh, uh-huh, uh-huh. I should have it here, but it is not here. Shit. Did I actually lose it? I had a network interface card of my very own. I lost. Shit. Shit. Fuck. I cannot find it. Let me look for it. Uh, okay, I will look for it later after the stream. I know I have it. I had a network. I guess that is a network interface card. It just gets into the Wi-Fi slot of a motherboard and it starts working. A MAC address is a unique identifier. A MAC address is a unique identifier assigned to a network interface card of a device. It operates at layer 2 data link layer of the OSI model. I have to understand the OSI model and is used for local network communication. MAC address structure. A MAC address is a 48-bit number typically written in hexadecimal format as six pairs of hexadecimal digits, because 48 is 6. 48 divided by 4 is 12. Oh, so 6 pair is 12 hexadecimal digits, like this or this. The first 24 bits, first 3 pairs, these 3 represent the manufacturer, OUI, organizationally unique identifier. Organizationally unique identifier. Okay, the last 24 bits, last 3 pairs are assigned by the manufacturer to uniquely identify the device. Okay, media access control, MAC. media access control. It is a unique identifier assigned to a network interface card of a device, NIC of a device, and it has 48. It is written using 48 bits. The first 24 represent the manufacturer, the last 24 represent a number given to it by the manufacturer, but that should not be enough, I guess. Yep, that just makes up the says that a manufacturer can make only about thousand, 10,000, 100,000, million, 16 million chips, which I suppose is not a lot. A manufacturer can make more than 16 million chips. They are a major manufacturer. And then device identification within a LAN. Switches use MAC address to forward Ethernet frames to the correct device. Uniqueness. No two devices should have the same MAC address on the same network. Through MAC spoof, though MAC spoofing is possible. Address resolution protocol. Maps assign IP addresses to map to MAC addresses so that devices can communicate on a LAN. Example in action, your laptop wants to send a packet to another device on the LAN. It knows the destination IP address but not the MAC address. It sends an ARP request. ARP, address resolution protocol. Hum, who is who has IP this? The device. It sends an ARP request, but who does it send it to? The device with that IP responds with its MAC address. This your laptop sends the data directly to that MAC address. Key difference: MAC versus IP address level. Data link, network layer. Purpose: identifies a device on a local network, identifies a device on the internet or a network. Uniqueness: globally unique but can be changed. Assigned dynamically or statically by network admin ISP. Globally unique but can be changed. MAC address is globally unique. Format 48 bits, 32 bits. Okay, MAC in MAC address, the last 24 bits um specify the first 24 bits specify the manufacturer and the last 24 bits specify a specific chip by the manufacturer and, but 24 bits can only represent about 16 million numbers. Then can a manufacturer not make more than 16 million chips, or if they do exceed 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 the limit, they can get another uh, number that will represent the first 24 bits and thus make the new chips under the new first 24 bits question mark. Yes, you have got the right idea. A manufacturer can represent multiple OUI organ organizationally unique identifiers. Organizationally unique identifiers if they exceed 16 million limit. How MAC address allocation works. The first 24 bits OUI, organizationally unique identifiers, are assigned to manufacturers by IEEE, Institute of Electrical and Electronics Engineers. The last 24 bits are assigned by the manufacturer to individual devices. Okay, last 24 bits are assigned by the manufacturer to the individual devices, since 24 bits can only represent 16 million unique numbers. A manufacturer who produces more than this number of devices will require another OUI. OUI is organizationally unique interface identifier, organizationally unique identifier from the IEEE standard, Institute of Electrical and Electronics Engineers. Institute of Electrical and Electronics Engineers, and the first 24 bits represent OUI, which is not the same as IOU, but this is organizationally unique identifiers. This new OUI provides them with another 16 million unique addresses to assign. 16 million unique addresses to assign. Example of a manufacturer with multiple OUIs. Apple has multiple OUIs because they have manufactured more than 16 million devices. Each new OUI assigned allows them to manufacture another 16 million devices. Another 16 million devices. Large companies like Intel, Cisco, and Samsung have dozens of OUIs. What happens if we run out of MAC addresses? Since the MAC address space is finite, the IEEE has introduced MAC address randomization and EUI, extended unique identifiers, instead of MAC for IPv6, which uses 64-bit MAC addresses instead of 48. Mhm. However, for now, allocating additional OUIs is the solution for manufacturers producing more than 60 million devices. Okay, okay, okay. So a MAC address is given to a Wi-Fi chip or to an interface which a device has to connect to the network, like which could either be Wi-Fi, Ethernet. What are the other Wi-Fi, Ethernet, or Bluetooth? I don't think Bluetooth. Wi-Fi, Ethernet. If MAC is a address assigned to the network interface, not the entire device. That means if a device has both Wi-Fi and Ethernet, it will have two MAC addresses, one for each interface. If a device supports multiple network interfaces, example dual band Wi-Fi for this for 2.4 gigahertz and 5, it might have multiple MAC addresses, one for each interface. Dual band Wi-Fi. USB to Ethernet adapters and visual network interfaces like visual network VPNs, virtual private network, virtual network interfaces. Virtual network interfaces also have their own MAC addresses. USB to Ethernet adapters, because they are also an interface, they also provide an interface. USB to Ethernet. Yep, because I will be able to use Wi-Fi and use a Ethernet cable through a USB port. Where is the MAC address stored? The MAC address is typically burned into the NIC, network interface card, firmware by the manufacturer. However, it can often be overwritten. MAC spoofing in software. Okay, would you like to check MAC addresses on your MacBook? Nope. Yep. Interfaces. Interfaces. What is an interface? What is an interface? For Wi-Fi, I suppose that there is a chip which um, can be put into a slot of my motherboard, and that chip has the hardware to send and receive Wi-Fi signals, bracket are just which are just a way to communicate over a specific range of the EM spectrum, which are just a way to communicate over the EM spectrum, and that chip on the motherboard gets a range of addresses assigned to the registers in it and through through manipulating those registers and reading and writing to them, the computer processor can indirectly send and receive Wi-Fi signals. Send and receive Wi-Fi signals through manipulating the contents of the registers. And since uh, so this is an interface uh, that is a way provided by a chip to communicate over a network. But since chip hardware chip architecture since Wi-Fi chip architecture can vary a lot, and it uh, would be really hard to load up into it would be really hard to write software that uses software it would be really hard to write software that that will access every network interface card network interface card successfully or successfully, and therefore the hardware manufacturer manufacturer or some third party organization writes a software called driver, which abstracts away the process of manually accessing the register contents of which abstracts away the process of manually accessing the register contents of a network interface chip, and it provides a standardized interface kernel to for the kernel to make use of the NIC chip. Well, I don't have to say NIC chip, that would be like network interface chip. Let's see. Yeah, you have described it well. Let's break it down step by step and refine the explanation of it. What is a network interface? A network interface is a point of connection between a computer and a network. Between a computer and a network that is very vague and abstract. It allows the device to send and receive data over a network, Wi-Fi, Ethernet, etc. A network interface can be a physical device, Wi-Fi card, Ethernet card, a virtual device, VPN tunnels, loopback interfaces. Okay, okay, let's go with it. How a Wi-Fi NIC works, the hardware NIC. Network interface card. A Wi-Fi card or NIC, network interface controller. Oh, it is network interface controller, not a network interface chip. Network interface controller is a piece of hardware that enables Wi-Fi communication. It operates using radio signals in a specific frequency, 2.4 hertz, gigahertz, or 5 gigahertz, or 6 gigahertz even. The NIC, network interface controller, has registers, memory mapped locations that store configuration settings, status information, and data buffers. The CPU communicates with the NIC by reading slash writing to these registers, which configures the card and sends slash receives packets. Sends receives packets. The driver software that controls the NIC. Every NIC has a different hardware design, making direct register access difficult across different models. A driver is a software that abstracts away the local details and provides a standard interface to the OS. The driver interacts with the NIC registers for control and data transfer. The kernel's networking stack, so user applications can send receive data easily. The kernel's networking stack. The kernel, example Linux, Mac OS, Windows, doesn't directly deal with NIC registers. Yeah, yep. Instead, it talks to the driver, which handles low-level details. The driver exposes a standardized API. Example. Shit, I cannot find my NIC network interface controller chip. Where could I have left it? Fucking hell. I want to find it. My NIC chip. It is fucking hell. Mm-hmm. It is. By the way, I have a motherboard right here, but I don't have my NIC chip. I have a whole fucking motherboard, but I do not have an NIC chip, which is sad. But once I will, when I do have that, it would be Pretty good. And right. Okay. So here, I don't know if you can see. Shit, you cannot can see now. Here, this is the processor. This is the processor with the covering on, and I suppose this is the ALU, and this you cannot even see it. And this is the ROM, which contains the firmware. The ROM chip is made by Winbond. The processor is by Intel, and yeah, the motherboard is by Cantel. Cantel, a Taiwanese company, and Winbond is also Taiwanese. And Intel processors, I don't know where they are made. It is, of course, American. It was like it is started in 1968, and with AMD and Intel started together. So that is cool. They are friends and rivals pushing each other to the limits. The kernel network stack, the kernel example Linux, Mac OS, Windows doesn't directly deal with the NIC registers. Instead, they talk to the driver, which handles low-level details. The driver exposes a standardized API example. In Linux, the kernel sees all the interfaces as /dev devices. CD / dev. Fucking it. Uh-huh. These are all the devices that are connected to my laptop. These are all the interfaces, right? Okay, this interfaces as devices. The kernel sees on all the network interfaces as devices in this. Applications like a web browser don't need to know anything about an IC hardware. Okay, a way to, I also have a remote connection to a Kali Linux server, which is, I just have to do this. I have already made a seg. I have already made a alias which I can use to connect to a remote Kali Linux server. It will just open in about 50 seconds. Applications like a web browser don't need to know anything about NIC hardware. They just use system calls to tell the kernel that they want to do something, and the kernel then in turn tells the driver that I want you to do something, which, and then the driver itself goes and manipulates the register contents of the NIC to make the NIC actually do something. Summarizing the layers: NIC register memory. Okay, kernel networking layer, networking stack, NIC. Okay, and now about the virtual part. A physical device, Ethernet adapter. Okay, um, just like a Wi-Fi, NIC. NIC is a chip that. Wait, yep, you are here. Press any key to continue. You have 10 seconds. Darn, you didn't press any key within 10 seconds. Try again, get a token. Ah, shit. I'll have to connect again. Ah, shit. I closed my terminal. Let me open it and connect again. Kali for connection to Kali Linux. And shit, I messed up the password. Password is segfault. 60 seconds. Here we go. And, and just like that. Yep. Yep. Just like a Wi-Fi, NIC is a chip. In the same way, and there is a chip that converts, that translates incoming and outgoing signals through an Ethernet through an Ethernet and gives an gives a register based interface. Creating server. Yep, server is on. I am inside Kali Linux, and I can cd dev ls, and these are all the devices that are connected. So nvim core. This file does not contain anything. We go to netrw and TTY. Okay, why are these empty and what do they represent? PTMX, PTS, something? Standard error. Standard error, standard in, standard out. Wait, okay, I have standard these. Okay, and this one has quite a bit of files. These are sockets, pipe, anon, ion, event, FD, event poll. It is using polling to do something. And why are all of these empty? Why the fuck are all of these empty? And there is nothing. Read only. It is not opening. Shit, it is stuck. Not my MacBook, but this thing. Kali Linux server. Yep, frames have not dropped. Okay, so I will have to stop the connection. Uh, and I'm using SSH for this connection. That is, I have a program that has opened a socket which is sending a request to a remote server, which itself has a program running which is listening on port number 22, and that program has some protocols which are called the SSH protocol, and I can send data which represents commands in Linux, and those commands will run on that other machine, and I can just do whatever I want with it. And this seems to have stopped working. Oh, moving on with this. Yes, an Ethernet and give a register-based interface to to read and to um, uh, to access the Ethernet connection, and to and the e and Ethernet itself, and and since Ethernet is a specification based technology and thus can't vary a lot, therefore uh, different OS OS manufacturers can write their own drivers to access an ether Ethernet interface or use someone else's driver or use someone else's driver. Yeah, that much we'll see. Exactly, you have got the core idea. Let's refine it a bit further. Ethernet, just like Wi-Fi and Ethernet and IC, is a hardware chip that handles communication over a hardware. So if I do not have a Ethernet chip, then I won't be able to do stuff with Ethernet. It translates incoming and outgoing electrical signals from the Ethernet cable into digital data for the computer. Yep, Ethernet and IC hardware. The IEEE Ethernet and IC follows IEEE 802.3 standards, which define how data is transferred over twisted pair cables. It includes registers that store configuration settings, status information, and buffers for data transmission. The CPU communicates with the NIC by read-write by reading and writing to these registers, just like over a Wi-Fi NIC standard protocols equals less variability, unlike Wi-Fi, which has different modulations techniques, frequency bands, and proprietary enhancements. Ethernet is highly standardized. Example, these three versions of Ethernet. Because of this standardization, an Ethernet driver is easier to write than a Wi-Fi driver. Who writes the driver? Since Ethernet NICs are more uniform in design, OS manufacturers like Linux, Windows, Mac OS, DBS is also an OS, can write their own generic Ethernet drivers that work across multiple NICs. NIC manufacturers NIC manufacturers Intel, Realtek, Broadcom. I have heard Realtek. I guess I have something by Realtek. Broadcom. I have heard Broadcom. Broadcast and communication. Many provide their own optimized drivers for their specific chips. Right, NIC manufacturers are. Intel also makes NICs along with processors. That is cool. Realtek and Broadcom. Open source communities often contribute drivers for Linux which get merged into the Linux kernel. That is cool. For example, Linux. Wait, what were daemons? Processes that always run in the background and do not require a terminal, an active terminal to run. Right. It is just so fun to just jump up and down in the abstraction layer. OS manufacturers and IC manufacturers, for example, Linux includes generic drivers like E1000 Intel and R8169 Realtek. Windows has built-in drivers for most Ethernet NICs. Seeing things with clarity is fun. macOS uses Apple's own drivers that can support, but can also support third-party NICs. Right, like the one I am using to connect to my laptop with a mouse and a keyboard, a wireless mouse and a wireless keyboard. The driver presents the Ethernet interface as a standardized network device. Example, the ETH0 or EN0 in macOS. EN0, the driver presents the Ethernet interface as a standardized network device. Standardized network device. It provides the driver presents. Okay, the driver does that, right? A driver presents the OS, the Ethernet interface. Interface is provided by the NIC, and there is a driver on top of the NIC which provides a standardized way and standardized network device. It makes the low level NIC represented as an interface, as an standardized network device interface. And these are called ETH0 or EN0 in Mac and ETH0 in Linux. Applications like browsers, SSH, etc. don't care about the hardware. They just use the OS network stack like syscall. NIC or Ethernet medium radio waves and this standard This uses this standard, and NIC Ethernet uses this standard. Hardware complexity more complex, and Ethernet is simpler. Driver variability, high variability, low variability. Who writes the drivers? Often manufacturer specific. OS can write its own drivers. Right. Fun thought. Wait, before or after the fun thought? Right now, I have a USB plugged in, a wireless USB plugged in to a adapter which converts that USB type to a C type, and that C type cable is connected to my laptop. And let's figure that out, how that is working. So on my Mac, which only has a USB port, which only has a C type port, uh, you shit. Looks like our message got cut off. Yeah, it did got cut off. A USB port and a C type port. USB to C type converter is connected to it. Let's handle that. How does that converter adapter works? Converter or adapter sounds like a better word. Adapter works. Right. Hum. Yep. Wait. What is a C type port? It works like this. So, oh, I do, but what I do have is a C type port. Right. Um. Right. Yep. Right here. Yep. Right here. A C type port, and this has two C type ports, and here it is. So it is a C type port, and it has a wire coming out of it, which can be connected to the motherboard. So I suppose what is happening in this thing is this okay, so let's just first of all talk about a C-type port itself. A port of C-type or USB type that a motherboard has mounted on it. Were How does a port of a mounted on it work? Now, my theory, I suppose that just like just like um, uh, there is a register based interface provided by just like there is a register based interface provided by the NIC chips. Similarly, there is a register based interface provided by a chip that handles USB or C type ports. USB or C type ports. USB or C type hardware ports and converts the incoming and outgoing zeros and ones into zeros and ones. No, not zeros and ones. Outgoing signals into register and data. And since these are very standardized, they have their drivers written by the OS manufacturer. Is that correct? Yes, you have got the right idea. Again, that is very fascinating that every device, no matter what, a Wi-Fi chip, an IC chip, a USB port, or a monitor, a keyboard, or a mouse pad, a camera, anything that the processor accesses, the kernel accesses through the processor is just data written in registers, which is the same way as you would use a processor through assembly language. That is cool. That is very eye-opening. Your Mac's USB port is connected to a USB controller chip, UCC. I guess this is a UCC. Yep. This chip handles communication between CPU and USB devices, flash drives, keyboards, Ethernet adapters, etc. Translates electrical signals from USB devices into data stored in memory registers. Translates electrical signals from USB devices into data stored in memory. Yep, my bad. Follows standardized protocols USB 2, USB 3, USB 4, Thunderbolt, etc., allowing the OS to interact with it in a uniform way. USB host controller hardware. The USB controller on your Mac is like a middleman between CPU and USB devices. The USB controller on your Mac is like a middleman between CPU and USB devices. It has memory mapped registers that CPU can read from, write to. These registers store device status. These registers store device status, control commands, and data buffers. These registers store device status, control commands, and data buffers. Yeah, data buffers make sense. Control commands, that is, you are accessing, you are receiving, or sending data. But how would, yeah, receiving or sending data? But it is not that something physically is going. Only the state of the wire is changing, which is a state change in the wire, that is high volt or low volt. It is not like you are sending or actually receiving something. The state of the wires which transfer data is changing from 0 to 1, which physically means change in the voltage level, and that we abstract away to be represented as zeros and ones. That is state change. I guess what control commands here means is that the state change, are you initializing that state change, or are you recording that state change, that is reading or writing? Data buffers in which you store that state change, and then can be read by the processor. And am I in the middle of the screen? Yes, I am in the middle of the screen, just like the middle of the night. Shit. It's been 1 hour. That is cool. And the CPU uses these registers to send and receive data from USB devices. To send and receive data from USB devices. Yep. Proper USB controller chips include Intel XHCI, extensible host controller interface. Is there something that I can see? It says vendor TMT, TMTYAA 4A1, and then some numbers. 2013. This is old and made in China. And vendor TMT. TMT Apple also has USB controllers. Okay, these are called USB controllers. What did it call them before? Handles communication USB controller chip. Yep, USB controller. These are called controllers, and in case of network interfaces, they are called network interface controller. Shit. Again, they are just called controllers. The hardware is called controllers in both the cases. USB drivers, softwares. USB is highly standardized, so OS manufacturers, Apple, Microsoft, Linux write their own drivers for USB controllers. The drivers interact with the USB controller registers and provides a high level API to the OS. For example, Linux has these, Windows has this, Apple has this for USB 2 and 3 and this. Right, the OS doesn't need to know about individual USB controllers, it just interacts with the driver. Yes, it does not need to know about the controllers. Controllers are hardware things, and drivers are the software which make communication with the hardware, with the controller hardware possible. Let's say you plug a USB to Ethernet adapter into your Mac's USB-C port. That is fucked up. How can I put in a USB to Ethernet adapter in a USB-C port? What happens? Physical connections. The USB device sends an electrical signal to the USB controller. Okay. Device enumeration detection. The USB controller detects a new device and reads its vendor ID and product ID PID from the device's firmware. PID vendor ID. Okay, I guess that is the vendor ID. YA4A1. Driver loading. If a driver is found, it is loaded into memory. Fucking hell. No, that is amazing. That is amazing. I want to understand what are microcontrollers. Microcontroller is a small computer on a chip that controls a specific function in a device. How is microprocessor different from microcontroller? Brief overview. A microprocessor is essentially just a central processing unit (CPU) on a chip, while a microcontroller is includes the CPU, memory, input, and output. Okay, microcontroller is system on chip. Mm-hmm. All right, and both of these are ICs, integrated circuits. Okay, okay, microcontrollers. How USB devices communicate with the OS. Yes, I have a physical connection, then a driver loading, data transfer. So, okay. Let's go a little more deep. Um, we are talking about controllers, USB controllers. So, the USB controllers, which are hardware devices themselves, are like little computers which are which run through a microcontroller and thus have their own IO IO system, memory, and processor. That is amazing if that is true. That is exactly amazing. That is exactly true. USB controllers are essentially small computers. So this this thing is a computer. Okay, either I am very stupid or this is not as complicated as I first thought. It says Acon and vendor is TMT USB controller. Yo, TMT hub, TMT company. It is a Dubai-based company. What does this do? This is electronics company. Yeah, TMT Global UAE. UAE is United Arab Emirates. Abu Dhabi is the capital. And company overview. What are the device products? Network cables, USB controllers, data pads, CCTV systems, fiber optics, coaxial cables, control and automation power, USB. Uh, USB controller. This is not the same TMT as this. Wait, is this the logo for TMT? And if it is, then this does not match that one, which I'm seeing on the screen. TMT, so this is not it. Let's go back to this learning. Exactly. Small computers embedded in your Mac's motherboard. They have their own microcontroller, CPU, memory, and I/O system, allowing them to handle USB connections independently from the main CPU. USB controller as a mini computer. A USB controller typically consists of a microcontroller, process USB signals, and manages device connections. Memory, RAM plus ROM, stores firmware and temporary data buffers. That is just amazing. And I guess there is a very small thing in here which must be the memory, a very small memory. Registers I/O interface. Registers are the I/O interface, and this interface is only open. Well, it is communicating on two fronts. One, the USB front, which the USB gets inserted into, and the other is the main computer, the motherboard. And for the USB front, it has the physical USB connection, and for the computer front, it has registers. Provides an interface for the main computer to send receive commands. PHY, physical layer interface, converts digital signals to electrical signals for USB cables. This means that when you plug a USB device, your Mac's main CPU doesn't directly talk to the USB device. Instead, it doesn't directly talk to the USB device. Instead, it sends commands to the USB controller, which then handles the communication. That is fucking amazing. Things, plots within plots within plots. How USB controllers work internally. Your Mac has a USB host controller that manages all USB devices. A Mac has a USB host controller. This controller detects when a USB device is plugged in, assigns it an address, fucking hell, an address, what type of device it is, manages data transfer between the USB device and the computer's main memory, handles power management, interrupts, error correction. The USB controller does all of this on its own without requiring constant involvement from the main CPU. Types of USB controllers. On your Mac, the USB-C ports are controlled by a USB host controller, which could be Intel, Apple T2 security. Some Intel Macs and newer Macs have Apple M1, M2 SoC system on chips. USB controllers. It has a built-in USB 4 and Thunderbolt controller. Okay, each of these controllers follow the XHIC extensible host controller interface standard, meaning Mac OS can interact with them using a standardized this driver. All right, I need time to process all of this, and let's just go a bit further. USB controllers versus USB devices. While your Mac has a USB controller which acts as a host, while your Mac has a USB controller which acts as a host, many USB devices also have their own built-in controllers. Many USB devices have their built-in controllers. Controllers are the things. Controllers are software. No, no, no. The software is are called drivers. The controller, yeah, controller is the chip. Controller is the chip that converts physical connections, physical incoming signals into register-based data, and drivers provide an interface for the registers to access the registers to the kernel. A USB flash drive has a small microcontroller that manages NAND flash storage. Fucking hell. USB USB keyboard mouse has a microcontroller that detects key press and sends signal over USB. Okay, okay, this is fuck. All right, all right. I guess I will write an article about how when I use my mouse, a wireless mouse, whose signals go from my mouse to a USB connected to a adapter which converts USB to Type C, and that Type C cable is connected to my MacBook. How does all of this works? So this is what is happening essentially. And now I have a wireless mouse. Hmm. First, let me describe the whole system at hardware level. I have a mouse, a USB to Type C adapter, and uh, a wireless mouse, a wireless USB which came with the mouse, and USB to Type C converter, and my MacBook. Let me try to explain how all of these are working in in unison to make to make the process of using my wireless mouse The process of using a wireless mouse possible. First, uh, 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 okay, I will describe each junction between all the parts. First, between the MacBook and the USB-C port. The USB-C port is a physical physical port which can be used to stuck in USB-C mail type USB-C type mail cables. Now the signals mm, mm, incoming or outgoing through this cable are translated into a register based interface which happens through a USB-C controller. Then that register based interface is translated into a standard software interface through a driver which is accessed by the kernel. Second, the USB to USB-C adapter. What the fuck is that adapter doing? The IEEE standard specified for USB-C is translated into the I IEEE standard for Type-C based communication. This is done with a microcontroller inside the adapter. This is done using a microcontroller inside the adapter, which also comes with ROM slash RAM. With ROM slash RAM in the conversion of USB to USB-C, from USB to USB-C means, wait, IEEE USB standard, what is it? 7 Universal Serial Bus. Shit, USB Universal Serial Bus chapter. Is this the official IEEE? IEEE Explore, IEEE.org. PDF. Yo, yep, PDF. I would like to have a PDF. N PDF. A PDF. Shit, I will have to. My institution? Shit. Is this not public? Standard PDF. Universal Serial Bus PDF. But there are different versions for it, right? HID Human Interface Device. Yeah, I heard that at some point somewhere. Interface intellectual property disclaimer requests report protocol. All right. Descriptors, operational model, functional characteristics, HID human interface department, human interface devices. Which revision history last written in 1920. Yep, 2020. Purpose. Okay, well, of course, I'm not going to read it fully. Yeah, the conversion of USB to USB to USB-C means conversion of physical signals, physical signals which adhere to USB signals into signals which adhere to USB-C protocol. Third, the connection between between the adapter and Wi-Fi USB that came with the mouse. Now, this Wi-Fi USB itself has a microcontroller within with its own memory and I/O interface, which is register based. Is it register based? No, this does not take signals out to the mouse, does it? Nah, it might. Based interface. This basically translates mm, uh, basically provides an I/O interface on two sides. One is USB based on the adapter side, and the other is Wi-Fi based on the mouse side, and the microcontroller in between the handles the conversion between USB and Wi-Fi. The USB signals are manipulated by the microcontroller through the USB controller and driver inside the Wi-Fi USB, and the Wi-Fi interface is accessed and the Wi-Fi interface is accessed through a Yeah, through a through a NIC, uh, through a Wi-Fi NIC chip along with its driver. And now on the last end, we have our wireless mouse. This has a microcontroller, a microcontroller, uh, and a microcontroller, a memory, and I/O interfaces, which consist of a which consists of a Wi-Fi NIC network interface controller, uh, mm, uh, position tracker, a movement tracer on the bottom, two buttons on the top on either side, and a scroll wheel. Yes, looking at and a scroll wheel. The microcontroller takes in input from the movement tracer. The two buttons and the scroll wheel, and through their own drivers, and converts them into a pre decided pre decided pattern of pre-decided pattern of zeros and ones, which is which is architectured by the mouse manufacturer, which is architectured by the zeros and ones, and sends them over to the Wi-Fi USB using its Wi-Fi NIC driver interface. Let's see. Your breakdown is almost spot on. You have efficiently outlined the hardware for flow for your wireless mouse, including all the key components and their functions. I will add a bit more clarification to each junction to refine the understanding and connection to all the tools. Writing a chat GPT query which cannot even fit in a page helps to clarify things in my own mind, just like Richard Feynman said that you have to teach, you have to teach, you have to teach. Not like three times, only one time he said that. So, yeah, has said it multiple times, but not at the same time. Maybe he did say that. I don't know. I wasn't there. MacBook and USB port. Shit, that is not. too long. Uh, okay. USB port C. As you correctly mentioned, the USB port C on your Mac is a physical interface and that allows data to flow between your MacBook and connected devices. It is a high-speed data and power interface. High-speed data and power interface. USB-C controller. This port connects to a USB-C controller in the MacBook, which manages the data exchange with the USB device. USB-C controller, the physical thing that takes in the incoming USB-C signals and converts them into a register-based interface. That is my understanding. This port connects to a USB-C controller in the MacBook, which manages the data exchange between the USB-C plugged in and USB device plugged in. It converts the incoming outgoing signals from the USB-C physical layer into a register-based interface that the OS can interact with. Okay. Driver, the USB-C controller driver example, Apple USB-C, HCI, USB X, HCI. Wait, there is a full form for XHCI, right? So my goal was to get into what all of this means, and I went to ChatGPT asking what does MAC address means, right? What was my first query? My router in the house acts as all of these things, and yes, my first query was based on this much here. Like it is a computer, it is just a computer. My router is just a normal computer. Right. Yeah, X H I. It was somewhere here. Hmm. XHCI. X. Wait. Ah, let me just read this. XHCI abstracts this low-level interaction providing a high-level standardized interface to the OS so the kernel can communicate with USB devices plugged into the port. USB-C, USB to USB-C adapter. Function. The USB to USB-C adapter allows a USB-A based device like wireless USB receiver for your mouse to connect to a USB-C port on your MacBook. Conversion microcontroller is in the adapter, microcontroller in the adapter, microcontroller in the adapter. Internally, internally this adapter has a microcontroller that converts the electrical signals between the two processors, between the two protocols. It handles signal conversion between USB-A, older standard, and USB-C, newer standard. While USB-C is just a new connector type, USB-C is just a new connector type. It can also carry USB 3x, USB 2 signals, meaning it can physically carry USB-A signals after conversion via a USB-C connector. Right, no driver needed for basic adapter. This adapter is purely passive in the sense that it only converts the physical connectors. It doesn't need its own driver. The underlying USB protocol is the same as USB-A, and your Mac USB-C controller driver can handle the data. Okay, the underlying protocol is the same, just the physical port changes. Okay, protocol is a protocol that can be implemented as USB-C or USB-A. Fucking hell, that is Eureka. Conversion. Okay, no driver needed. I will ask about that. This. wireless USB-C receiver. Yes, USB-C wireless receiver. And the this device is a USB dongle connected via USB-A that interfaces with your mouse wirelessly. Microcontroller. The microcontroller inside the inside the wireless USB receiver handles the interaction between the USB protocol. The microcontroller inside the wireless USB receiver handles the interaction between the USB protocol used on the computer side and the Wi-Fi communication used between the receiver and the mouse. The Wi-Fi and IC interface. The microcontroller manages the conversion between USB-C protocol and Wi-Fi communication. Between the conversion between USB protocol and Wi-Fi communication. USB protocol and Wi-Fi communication. The receiver's Wi-Fi NIC network interface controller chip allows communication with the mouse using Wi-Fi, likely a simple wireless protocol, not full-fledged Wi-Fi, but more of a low-power wireless communication like 2.4 gigahertz driver. The USB to Wi-Fi microcontroller. The USB to Wi-Fi microcontroller. USB to Wi-Fi USB to my Wi-Fi microcontroller inside the receiver in the receiver is handled by the OS using a driver specific to the USB to Wi-Fi receiver. Fucking hell, yes, that itself has a fucking OS. The OS will communicate with this microcontroller using a USB interface which is abstracted by the driver. Shit. It itself has an OS. All of this is fucking amazing. My mouse has an operating system of its own. My keyboard has an operating system of its own. Fucking hell. Wireless mouse. Mouse components. Fucking hell, my mouse has an operating system of its own. Fuck, my keyboard has an operating system of its own. Shit, my router has an operating system of its own. This Wi-Fi to USB this thing has an operating system of its own running on it. That is amazing. Shit. Every computer that is running a microprocessor has an operating system of its own, at least a kernel, which the high level processes the application, if you could call them applications, the daemons, I guess you could call them, the daemons running use to access the physical hardware using syscalls. That is fucking amazing. Wireless mouse. That is literally fucking amazing. Wireless mouse. Actually amazing. Wireless mouse components. Movement sensor. Optical LED captures the movement of the mouse over the surface. Button and scroll wheel provides the input. Pressing the mouse button and scrolling the scroll wheel. These inputs are converted into digital data, usually a specific pattern of zeros and ones by the microcontroller. Microcontroller in the mouse. The mouse has an internal microcontroller responsible for processing the inputs from the movement sensor, buttons, and scroll wheel. The microcontroller, yes, scroll wheel. The microcontroller encodes the movement data, example, movement, direction, button press, and scroll wheel activity, prepares it in a standard format, likely a packet of data represented by the mouse's state, transmits the data wirelessly via the mouse's Wi-Fi NIC to the receiver. Wi-Fi NIC in the mouse. The Wi-Fi network interface controller. Wi-Fi. I have to repeat these things like multiple times so that I remember them later. Wi-Fi interface controller. The Wi-Fi network interface controller. Wi-Fi network interface controller. the hardware fucking physical thing, allows the mouse to wirelessly communicate via the USB receiver. And I suppose now we are with the USB-C receiver, which is plugged into your MacBook. This NIC interface with the Wi-Fi network used by the receiver, but it's typically a low power wireless communication, not the regular full Wi-Fi. Yeah. Driver in the mouse. The driver for the mouse inside the mouse is firmware input from the mouse sensor button and scroll wheel and converts it into the communication protocol understood by the USB receiver. Full process recap. Mouse input movement clicks are processed by the mouse microcontroller. Are processed by the mouse microcontroller. Fucking interrupts after interrupts after interrupts. Interrupts within interrupts within interrupts. Not within, but sequential. Sequential interrupts. Sequential interrupts. The same way that have been faced by the Hebrews. The microcontroller encodes the input data and sends it via Wi-Fi to the USB receiver. Sends it via Wi-Fi to the USB receiver. Yep. The USB receiver with a microcontroller and Wi-Fi NIC. The USB receiver, yep, right there with a microcontroller and a Wi-Fi NIC. Wi-Fi NIC receives the data and converts it to USB protocol. Yep, the USB to USB-C adapter, if necessary, passes the data through the USB-C port on the Mac. The USB controller on the Mac translates the data into a register interface, making it accessible by the USB driver. Yep, the kernel communicates with the USB to process the mouse data translated into actions like cursor movement, clicking, etc. Conclusion to I have to yep. In essence, the process involves multiple microcontrollers, one inside the mouse, one inside the receiver, one inside the adapter, working through to translate input signals into a usable format for your MacBook. This communication is wireless between the mouse and receiver using a custom Wi-Fi protocol, but then becomes USB based to interface with your computer. Would you like further detail? No. One more thing. Apple. One more thing. Yep, this. Hmm. The USB protocol specified by IEEE is just a protocol which can is just a conceptual structure conceptual structure which specifies standard standardized way for communication between two devices. In this conceptual structure can take birth can take physical form in the form of uh, can take a different physical forms like USB A and USB C. If that is true, that would also be fucking amazing, and it is true. USB C protocol conceptual structure. structure. The USB protocol itself is a conceptual framework or a concept or a set of standards that define how data is exchanged between devices, how devices are powered, and how they are identified. It is specifies the communication rules, data formats, power management, and other details that govern how devices like keyboards, mice, storage devices, printers, etc., interact with a computer. The USB protocol defines the logical structure of communication, including data transfer modes, packet structure, addressing. Okay, what am I reading? What the USB protocol defines? Logical structure defines. Yep. Uh, Data transfer modes, packet structure, addressing, power management. Power management, addressing how each device is identified. Yep. Okay, I can go much more deeper. Exactly, pretty deep. I literally, at this point, only have scratched the surface of communication, of networking communication. This is so fucking fascinating. Power management, how power is supplied. But I do not want to take in too much information because that just I've seen messes up and is not really good always. Device enumeration, how devices introduce themselves to the computer. How devices introduce themselves to the computer. Yep, yeah. Shit. Narrative. Where is the narrative? Different physical forms. Yep. The USB protocol doesn't specify the physical connector types. Rather, it allows for different different physical connectors to be used as long as they follow the common rules set out by the protocol. A USB-A, this is the older rectangular connector that has been widely used in computers and peripherals for many years. It is commonly seen on computers, laptops, and USB hubs. USB-C, this is a newer, reversible, smaller, and more reversible because like it can be put in any orientation. It has like it repeats itself after 180-degree rotation in a certain direction. It is a newly reversible, smaller, and more versatile connector that supports higher data transfer rates and power delivery standards. It's gaining popularity in modern devices, including laptops, smartphones, and peripherals. How USB-A and USB-C relate to the protocol. USB-A and USB-C are simply different physical connectors that carry the same underlying USB protocol. USB-A connects using the older USB specifications like these, but it is the same protocol as USB-C, just in different form. USB-C can support higher speeds like these Thunderbolt 3 and more advanced features like power delivery, faster charging, but it's still using the same USB protocol at logical level. Adapters and compatibility. Adapters are used when you need to connect a USB-A device to a USB-C port or vice versa. The adapters don't change the protocol. It simply converts the physical layer, example connector, between two types. Once the connection is established, the underlying USB protocol is the same regardless of whether it's a USB A or USB C. Okay, okay, that is a bit, yeah, okay, okay, that is a bit of information, right? I guess what have I learned about routers? That everything is just a fucking computer with a microcontroller, memory, and input-output peripherals. That is a very important thing, and the communication between a microcontroller, the processor inside a microcontroller, and the peripherals, or anything for that matter, the I/O devices or the memory, which are the only devices that it communicates to, or maybe the ALU, that is, it just sends signals through an address and signal bus there, and the data bus signal bus, yeah. It happens through register addressing. the input output peripherals, and the memory is mapped onto the addresses, onto addresses, right? And who manages the addresses? The OS, the kernel manages the addresses. Yes, who the fuck manages the addresses? Drivers. Okay, fucking hell. Okay, okay. I guess uh, hmm, who manages the addresses? Wait, what I think is that it is the kernel who manages the addresses. In all of this, it's the kernel who manages the addresses. Who, it is the kernel who manages the addresses for the memory and the peripheral devices for the memory and the peripheral devices, and and this addressization addressization is itself an illusion, and it is itself an interface provided interface. But the address level thing is managed by the kernel itself, so why would it make an address based interface for itself so that it can itself manage those devices properly? Addressization itself is an interface built by the kernel to be used by itself, uh, to be used by itself, to be used by, yes, built by the kernel to be used by itself, to make some abstractions. Yep. And when an application software wants to access these, it just makes a sys, sys call to the OS kernel. Fucking hell, fucking hell, fucking hell, fucking hell, fucking hell, fucking hell. Yes, you are on the right track. Fuck. Oppenheimer music going in my head. The kernel plays a crucial role in managing hardware resources and abstracting them by use by both the system and application software. Here is how it fits into the picture. The kernel plays a crucial role in managing hardware resources and abstracting them. The kernel plays a crucial come into the present. The kernel engage. Unlike Paul Atreides who says disengage, I say engage. The kernel plays a crucial role in managing hardware resources and abstracting them for use by both the system and application software. Both the system and application software. The system means the rest of the OS without the kernel. Here is how it fits into the picture: kernel and memory management. Memory management is one of the core responsibilities of the kernel. It manages all available memory, both RAM and virtual memory, ensuring that writing in OS is going to be fucking amazing. And writing a compiler is also going to be fucking amazing. Cannot wait. A long process. Yeah. It's going to take a lot of time. A long way at right now. I'm here running this, ensuring that each process, all I have to keep in mind is to do not stop. Yep. And important things will keep repeating themselves, and I will keep investing into them, and my cognitive map will start to come around, and it will start to get more detailed as I keep going. And details not stop presenting themselves to me. So my cognitive map become will start to increase its resolution, ensuring that each process gets its own isolated address space. Each process gets its own isolated address space, that is virtual memory, and that different processes don't interfere with each other. That is handled by the kernel. The kernel uses paging and segmentation to elevate and manage memory, translating virtual memory address is used by applications into physical memory addresses on the hardware. The kernel also manages I/O operations between devices and applications, ensuring that hardware devices like network. Ah, fuck, I just fucking skipped that line. The kernel also manages I/O operations between devices and applications, ensuring that hardware devices like network cables, network cards, NIC, network interface controller, USB controllers, storage devices, etc., are associated in a safe, controlled manner. Peripheral device management. The kernel provides an interface for managing peripheral devices like USB controllers, network adapters, which is network interface controllers, and other I/O devices. This interface abstracts away the low-level details of accessing and controlling the hardware, making it easier for applications to interface with devices without worrying about the hardware details. When you plug in a device like your wireless USB dongle, the kernel detects it, assigns it an address or identifier in its device tree, and sets up appropriate devices drivers to manage the communication with that device. These drivers may assign files like device files like dev USB 0, and the kernel handles their low level communication. All the devices are in slash dev. All the devices are in slash dev. Where the fuck is my terminal? Right here with David Goggins. Uh, yep. Um, cd slash dev. That are all the devices connected. And why are these empty? FD file transfer, monotonic, Unicode. Why are these empty? Zero. Well, that I guess should have zero. Okay, why are these empty? These were empty in the remote Kali server also. Address space and syscalls. The kernel maintains the address space for processes and devices. When an application wants to interact with the hardware, it can directly access the device's memory or registers. Instead, okay, so physically there are registers, and the OS maps them The when the OS itself wants to interact with them, it uses its address-based system to access them, and if it wants to provide an interface to application processes, it gives them syscall interface to do that. To request the kernel to handle that interaction. For example, memory access. If an application needs to allocate memory, it will use the malloc syscall. If yeah, if it wants to access memory, yes, memory is a fucking hardware device. The RAM, if a device wants to access RAM, it has to communicate with the OS, and to do that, it makes a syscall. If an application needs to communicate with a device like a network card or USB, it uses higher level syscalls. System calls like read write IO CTL, IO control to interact with the kernel. The kernel then communicates with the device drivers and handles the actual IO. Fucking Eureka after Eureka. Device drivers are special pieces of software that allow the kernel to communicate with hardware. They provide the kernel with a standardized way to interact with the devices and abstracting the underlying complexity. Each device, like a USB controller, network adapter, etc., requires a driver that is loaded by the kernel when the device is detected, and the driver is contained in the firmware chip of the device of the controller. The kernel uses drivers to translate high-level requests from the application software into low-level commands that the device understands. For example, if an application wants to send data over a network, it calls appropriate sockets calls. Like these, the kernel then delegates these actions to the network driver, which handles the communication. Okay, I started reading about all of this because I wanted to understand why my IP is not global, but I've gone like below the abstraction layer, which doesn't even know about privacy and access and stuff. So I will have to come up the abstraction layer and find the layer where the stuff I want is happening, and for which I will be exploring this in, I guess, the next stream. Kernel abstraction for devices. The kernel provides a consistent abstraction layer for all hardware, enabling applications to interact with. Wait, fuck, skipped the line again. The kernel provides a consistent abstraction for all hardware. Uh-huh, uh-huh. For all hardware, it means abstraction layer for all, not for the hardware, but to the hardware. It provides it to access the hardware. Yeah, it can, but I get it, okay. The grammar, I get it. Enabling applications to interact with devices without needing to know the hardware details. For example, the kernel may abstract USB, Ethernet, or wireless communication as file-like objects with device file, making them appear as regular files to use applications. So this is simplifies application development and also summary. What did I read in this paragraph? In this whole response, that the kernel provides the syscall interfaces for the applications to interact with the hardware devices, and for itself, it uses the drivers. And yep, the main thing is the virtual memory, which is managed by the kernel. Right, right. Which is managed by the kernel. Yep, that's cool. That's cool. And that is it for today's stream. That is fucking it for today's stream, I guess. Not I guess, I no, that is shit. Uh, why are there two streams with this fucking same? I didn't update it. My bad. My bad. Yeah, that is it for today's stream, and bye.